Welcome to Lecture 2. Following the discussion on the scientific method, this lecture will focus on the criteria scientific theory should have to be considered good.
Is following the scientific method sufficient for our scientific investigation?
It is insufficient. We must go beyond it from time to time to answer questions such as, how should we compare theories devised to explain the same phenomena? In many cases, different theories compete to explain the same phenomena.
Theories should be less favored if their predictions are not in line with experimental results.
But what if multiple theories agree with all experimental results available? Another question that the scientific method doesn't answer is, what qualifies as a good theory?
Well, the scientific method requires us to constantly check predictions from a hypothesis against experimental tests. We also learned how we use inductive reasoning to come up with a hypothesis and ensure our conclusion is reliable.
But a reliable theory is not necessarily a good one.
Let's see what Feynman thinks good theories should look like.
I must also point out to you that you cannot prove a vague theory wrong. If the guess that you make is poorly expressed and rather vague, and the method that you use for figuring out the consequences is rather a little vague, you're not sure, I mean, you say, I think everything's because it's all due to Muggles, and Muggles do this and that more or less, so I can sort of explain how this works. Then you see that that theory is good because it can't be proved wrong. If the process of computing the consequences is indefinite, then with a little skill, any experimental result can be made to look like an expected consequence. You're probably familiar with that in other fields. For example, A hates his mother. The reason is, of course, because she didn't caress him or love him enough when he was a child. Actually, if you investigate, you find out that, as a matter of fact, he did love him very much and everything was all right. Well, then, it's because she was overindulgent when he was a child. So by having a vague theory, it's possible to get either result. Oh, wait. Now, the cure for this one is the following. It would be possible to say, if it were possible to state ahead of time, how much love is not enough and how much love is overindulgent exactly, and then there would be a perfectly legitimate theory against which you can make tests. It is usually said when this is pointed out, how much love is and so on, oh, you're dealing with psychological matters and things can't be defined so precisely. Yes, but then you can't claim to know anything about it.
This time, Feynman has told us that a good theory cannot be ambiguous.
Feynman seems to have strong opinions on social science, and I'm sorry if you feel offended by this, but hopefully you can understand his idea that predictions from our hypothesis should be as concrete and precise as possible.
This means stating clearly what would happen and what to expect if others are to carry out certain procedures.
Exactly. For example, it would not be very useful if a financial analyst told you that the stock price of a certain listed company is going to rise in the near future. You would not know when to buy the stock, let alone when to sell it to make a profit.
Instead, the financial analyst should provide more concrete buying and selling strategies, but unfortunately, this seems to happen very rarely. How can we ensure our hypotheses are concrete and precise?
One way is to use mathematics. This will be further elaborated in our lecture on mathematical modeling, but for now I want to introduce a very concrete scientific theory, quantum electrodynamics, or QED.
What is quantum electrodynamics?
QED theorizes the behavior of electrons in light and how they interact with each other. However, the theory is not a focus of this course. Rather, we encourage you to look for your own examples of concrete theories during your scientific investigation journey. This theory contains a parameter called the fine structure constant, which represents how strongly electrons and light influence each other. This fine structure constant turns out to be one of the most accurately calculated parameters in science through both experimental measurements and theoretical predictions.
As of 2025, the reciprocal of the constant alpha is determined to be this number. The number in the parentheses means that the last two digits of this quantity, 77, are subject to an error of 21. This implies a precision better than 1 part in a billion.
We can have a better sense of the precision this number represents by imagining the same level of accuracy for determining the population of a certain country.
Such a precision would mean we are confident that there are exactly 1 billion citizens in a certain country, not one more or one less.
Feynman was one of the important figures who established QED, and his preference for a theory being unambiguous should be convincingly demonstrated in this case. Let's look at a theory from economics that isn't as concrete and precise. A key area in economics is buying and selling behavior, and it requires understanding why or how we make choices between different goods. Consider going to the HKU CYM canteen. Would you choose rice or noodles, Curio? One way for economists to understand why or how we make choices is through a concept called utility, which is defined to be the amount of satisfaction one would get from consuming a certain product.
Well, having a bowl of fried rice would give me 70 units of utility, while a bowl of noodles would give me 90 units of utility. Since 90 units is greater than 70 units, a bowl of noodles would give me more satisfaction.
And I believe you are rational, Curio, so you would choose noodles over rice.
I notice a few problems with understanding choice-making with this concept of utility. Can this really help us predict how many customers will prefer noodles over rice at the CYM canteen on a particular afternoon?
This brings us to why using the theory of utility to make predictions has some issues. Firstly, such a utility function can vary for different people because we all have individual preferences. A serving of rice and noodles may give you 70 units and 90 units of utility respectively, but I receive completely different amounts of utility upon consuming the same goods.
Then, to predict how many people would prefer noodles over rice, we would need to know in advance the utility function for everyone.
Exactly. Secondly, even for the same person, the utility function can be quite different at different times because our preferences change.
Today I prefer ramen, but tomorrow I may find curry with rice more attractive.
So, to make predictions about how many customers would pick noodles at a particular time, we would also need to know how people's preference changes over time. As this theory generates different results based on different customers and different days, utility isn't a concrete and precise theory.
Examining the examples of QED and utility has hopefully prompted you to think about what scientific theory should have to be considered a good theory.